This is the part 2 of the concept of the photoelectric effect and its demonstrations. So, for those who haven't seen yet the part 1, I would recommend to see first the part 1 to ensure the concept of the photoelectric effect. This video is focusing on the demonstrations, and let's perform the experiment using our photoelectric effect apparatus. So, okay, let's do the experiment. This is the video clip of our actual apparatus. This is coming from the Pasco Science Star company, the photoelectric effect apparatus. So, I have here the tumbler of the Pasco distributor, and we have the corporation is Science Star. Now, in the apparatus, this is the source of light. This is a mercury lamp. The light is going to shine the photodiode on this target. This is the power supply of the mercury lamp, and this is the photodiode box. Inside the box is the photodiode element, which is the target of the light. Inside the box is the photodiode. This is the picture of the photodiode. The light will shine onto the surface, then it goes directly to the photodiode. Then the escape electrons will travel to this wire. Then everything will be recorded on the voltmeter and its current. This is the voltmeter and the ammeter, and this is the interface. So in the photodiode, we have, before going to the light goes to the photodiode, it enters first in the filter wheel with different or 5 different wavelengths. So we can adjust the wavelength of the light going through the photodiode in 5 different wavelengths. So you just turn the aperture. With the aperture, we have the wavelength, and this is the voltmeter. So this will control or measures the voltage coming from the photodiode whenever there is current that pass through the or ejected, then it will be recorded. The voltmeter also will serve as the source of energy to control the current flows from the photodiode. So remember that we can control this in such to stop the electrons from moving to the circuit. And this upper element is the ammeter. This is to measure the current. So if we see a number here, it signifies the current. So we can read the current, and we can also, by changing the amount of the potential, stopping potential, then this ammeter will set to 0. So the meaning of 0 means the electron stop moving from the cathode of the photodiode, will reach to the anode point, then stop. Or from the cathode, or from from the anode, which is the photodiode, the electrons will travel towards the cathode, and it will stop through adjusting the knob of the voltmeter. So you have to recall our first video. That in our first video, we have the source of light, and this is the setup that they use during the verification of photoelectric effect. And this will be the setup also used for this apparatus. So recall on those, for our first video that this is the target element. This is target wherein the light shines to that surface, then electrons will be ejected. So once ejected, it will move towards the cathode, but take note that if this is cathode and this is the electrons, which is also negatively charged, then this will be this electron should be repelled. But because of the stopping potential, we can adjust this one in such that this electron is about to reach to exactly at that point, but no longer current that flows to the circuit. So the stopping potential played an important role because when the light shines to the surface, the electrons will be ejected, and that electrons ejected will goes through the cathode point. The cathode point can be controlled using a stopping potential in order that these electrons will reach at that point exactly with no current observed. So how did we know, or do we know that this current is zero? So we have here the ammeter. This is the ammeter. And adjusting the potential, stopping potential is the voltmeter. So we will adjust the knob here and look for the number on the ammeter, and this should be adjusted to 0 because once the light is shined to the surface, you can see, you can observe the values here, and it is greater than 0. So all we need to do now in order to produce a zero current, so that we can assure that these electrons will stop at that point, we will adjust the stopping potential in order to set this ammeter to be 0. So in that case, the electrons is about to end at that point only. Remember in our lecture, first video, that the exit velocity, this is the kinetic energy final, which is the maximum, and it will be reduced until 0 at that point. The final kinetic energy becomes 0 only if that electrons will stop at that point. So how would the electrons stop at this point? So it is because of the stopping potential. If we will not control the stopping potential, then the electrons will travel to this current. Okay? So again, this is the target. And target is inside the box of the inside the box is the photodiode. This is the photodiode. Approximately, this is facing on the left side, but this one is facing on the right side. So this is the curved element. The photodiode is somewhere in this point, and this is the voltmeter. Also, the other wire is the exit electrons while traveling from the anode part, and this is the cathode part. And again, this is in our system, or at our setup previously in our first video, this is the stopping potential. We adjust this one. So doing that is to rotate this knob and observe again this one to become 0. So this will become 0 only if we will adjust the knob of the voltmeter, and this is again the ammeter. Okay, so this is our experimental data. In the experimental data, we need the wavelengths. So in our apparatus, we have different wavelength. We have the different wavelength. So when the light enters to this point, these numbers in the upper part will be wavelength of the light as enters to the mercury lamp will strike at that point. Then as it enters to the diode inside the box, the wavelength was set to this number. And then we will rotate this one, rotating this one by changing the wavelength. And there are 5 different wavelengths that we can observe. Okay? Remember, this is the setup. The light, this is the source of light. The mercury lamp will strike to that point. Then enter to the aperture where we can adjust the wavelength. Then after that, the voltmeter was connected to the element, the anode part and the cathode part. Then we can see the voltage reading here. And this line, this wire is the wire, this is the line that the electrons, the ejected electrons will come through this wire and goes to the ammeter, so that there must be a reading at this point. So again, as I've said, there are 5 different wavelengths in the aperture of our apparatus. So first we will set the wavelength into 365. This is nanometer, very very small wavelength. And this is, the next is we will rotate the knob and adjust that to 405 wavelength. Then next to 436, then 546, and finally the wavelength of 577. Now, with this wavelength, we can find the frequency. If you remember our previous video, that the energy of the photon is a function of frequency, because it is the principle of the photoelectric effect introduced by Albert Einstein, that the energy of the photon is proportional, directly proportional to the frequency. It is different from the Maxwell's and other physicists, that they say that light is a wave. So they say that the energy of being as a wave, the energy is, or the photon depends on the intensity. But in the concept of particle, light as a particle by Einstein, the energy of photon depends on frequency. It does not depend on the intensity. So they have different ideas, but the two ideas are correct, because we will use the concept of intensity for the energy if we treat that as a wave. But if we treat that as a particle, then we will use the concept of the frequency, dependence of the energy of the photons. Okay, so the relationship between the frequency and the wavelength is, take note that the speed of light is equivalent to the frequency times the wavelength. So therefore, if we take the, or solve the frequency in terms of the wavelength, then it is C over the wavelength. So substituting the value of wavelength here, and remember that the speed of light is 3 times 10 raised to 8 meter per seconds. So using this formula, replace this, then we have the equivalent frequencies for different wavelengths. So in our experiment, all we need to do is to find how much is the stopping potential. Take note that this is the voltmeter. So how can we say that it is a stopping voltage or stopping potential? Okay, so we will rotate this knob again and then observe the data on the ammeter. Then this must be 0. So if this is 0, automatically whatever readings on the voltmeter will be our stopping potential. And take note that once we set the five different wavelengths, then D must have different potential, different stopping potential. So because therefore the current will be changed here. So therefore you must always set the voltage adjust for every changing of the wavelength of the light. So let's go. Let's proceed the experiment. So again, once the light strikes to the target into the photodiode, then first is we will set the wavelength into the 365 nanometer. So adjust the wavelength here. The light strikes, adjust the light. Then after that, use this one. Take note, this is a 305 wavelength, and the corresponding reading on the voltmeter. Once we adjust this one, this number is 0.001 is approximately 0. In the actual experiment, this is fluctuating. Actually, we cannot exactly say it 0, but this 0.001 is very close to a 0. So therefore, we had already adjusted here in such that this will become approximately 0. So therefore, in our first trial, first wavelength for the 365, after turning the knob of the voltmeter, then observing this to 0, then the reading is negative 1.78 volts. So the negative means it is the stopping potential. Do you remember that in our first video, we reversed the polarity of the source, reversing in order to have a stopping potential. So this negative means it is the reverse voltage. Okay, then in the next trial, we will change the wavelength of the light by rotating the knob, rotating the aperture. By the way, whatever reader should be placed in the under the line of the 365. So the unit is volts. So then rotate again. Now this time the wavelength now is 405. So 405. Then we adjusted the knob here. So after rotating this, changing the wavelength, there is a number on the ammeter. So what we did is we rotate this knob until 0 and we observe another voltage. Oh, remember, previously for the 365, the voltage reading here is 1.78. Now, after rotating to 405, this will the same. Okay, this is the same, but because we want, but okay, the same voltage, but it has a current here. So, meaning to say that during the time the electron travels to the circuit, it forms a closed circuit. So, we want to stop the electrons at exactly towards the anode part or the cathode part point. Or therefore, so we adjusted the knob, then the result is 1.376. So, this data will be placed here in this point. So therefore, for the 365, the stopping potential is 1.78, while in the 405, the stopping potential is 3.76. Okay, so in the third trial, we rotate again, proceed to the next wavelength, then this is now the 365, 436, sorry, 436. So with a frequency of 6.88, 0.73 times 10 raised to 14. Then take note of the voltmeter again. So we adjusted and set this to 0. So therefore the stopping potential at that wavelength is 1.25, negative 1.25. Then do it again, the same procedure. Adjust now in the fourth trial 446. Then observe the reading. It is keep on decreasing. The voltage is decreasing from 1.78. Then in the fourth trial, we have only a value of 0.683. So do it again, rotate again. Then we have the wavelength of 577, and take note the reading is reducing again to 0.56 volts. So here, so this is the complete data. So with this data, what we did is we will verify this experiment using this data. We will verify if it is true that the electron liberated from the surface of the photodiode. So if it is true, then therefore we will verify the accuracy of this apparatus. So in this result only, this shows that electrons was liberated or escaped from the surface. But how true or how credible are the data produced from our apparatus? So in order to verify the accuracy of the apparatus, then we will solve the Planck constant. We will solve the Planck constant using this data. Remember, in our previous video, the energy of photon is equal to the Planck constant times the frequency. So therefore, then we produce a linear relationship with stopping potential with the frequency. And remember that we have this stopping potential and we have this frequency, and the material is a photodiode. So with this data, we can verify, we can calculate the actual or the Planck constant using the data. So if the result coming from this data is very far from the Planck constant, then our apparatus or our data is not an accurate result. So therefore, all we need to do is to graph the result. So we will graph the result because this is the stopping potential on this axis, while on the horizontal axis is the frequency. Take note that the stopping potential depends on the frequency, and this frequency is actually proportional to the wavelength, inversely proportional. The greater the wavelength, the smaller the frequency. Take note, this is 577, but we have only the frequency of 5.1991 times 10 raised to 14. And our 365 is 8.21918 times 10 raised to 14. So it is inversely proportional. So plotting all this data, the frequency versus the stopping potential versus the frequency, and these are the observed points, and this is approximately a linear. So with this result, this shows this is approximately in a straight line. And in our derivation in the first video, that the relationship of the stopping potential is linear relationship with the frequency. So all we need to do now is to find the equation of this line, or we will regress this using statistical methods. We will create an equation coming from this, then it should be a linear relationship. Now remember again in our previous video that the coefficient of the frequency is the slope, and the next term is the Y-intercept. So therefore, if it is a slope, and the slope is h over e, do you remember? Can you recall the video? Our stopping potential V is equal to h over e multiplied by the frequency plus the work function divided by the E, which is the charge of the electron. So, the slope of Planck constant divided by E, which is the electron, we can equate that with the slope of this line that we will raise later, then solve for the Planck constant. So therefore, based on the regression output after curve fitting with r squared of very close to 1, so meaning this equation is very close to the points, and this is a linear. So y, which is this one, is equivalent to negative. Negative means it is open to the left in our data. And this is 4 times 10 raised to the 15 x. So x is the independent variable. In our case, this is the frequency. Y is our stopping potential. And this is the slope. Okay? And this is the Y-intercept. So if you remember, again, going back to the first video, the coefficient of the first degree variable, which is the frequency, is the Planck constant divided by E. So go back to the old video or previous video. And this is the work function divided by E, which is our Y-intercept in the linear principles. So the slope based on this regress equation is negative 4 times 10 raised to negative 15. We can ignore the negative sign. And the unit should be joule secant per coulomb, because the result should be volts. And this is frequency. Okay? So this must be joule secant per coulomb. And take note again, this is h over E, where h is the Planck constant. So remember that the value of E is known as 1.609 times 10 raised to negative 19 coulomb, the charge of one electron. So one electron charge is known, and this is the slope, which is also known from the equation. So we can solve the Planck constant. So this is our value of the Planck constant using our data. So after calculations, by the way, the Y-intercept again is 1.4917. So this is, we will utilize the data here. And take note that the Y-intercept is what? If the slope is h over E, the Y-intercept is what? The work function divided by the electron. So therefore, again, if you want to know how much is the work function of the photodiode, then we can theoretically solve that by calculations. This is E again, multiply by this value. So we can solve for the work function. Remember, our previous video, the work function is the energy on the electrons inside the metal. It is the amount of energy that holds the electrons in the position of the metal. And here comes the light that strikes to the surface. He attempts to remove that force from the electrons in order to escape. So therefore, there must be enough, in order to liberate the electrons, there must be enough energy to overcome this work function. So in our experiment today, we are able to calculate the amount of energy that holds the electrons in the position of the metal surface. So, therefore, we can calculate. So, what's the use of this? The use of Planck constant is to verify. While this one, after calculating, we will compare this data with because our photodiode is mostly sodium, and we have results in the different experiments for the sodium. So we will compare that result and let's see what's the result. So therefore, again, do the calculations. So after calculating this one, E, which is 1.602 times 10 raised to negative 19 coulomb, multiply it this one, then the unit becomes joule secants. And this is the unit of the Planck constant. So the result is 6.408 times 10 raised to negative 14. Okay? Compare that with the accepted. Look at the result. The result the result is very close. We have this is the accepted. This is the constant based on the give or experiment from the other one physicists. So the result is 6.626 times 10 raised to negative 34 joule seconds, and here comes our experimental. If we compute the error or the percent difference of this is 3.29%. So a very, very close. So how can we say about our apparatus? Then it is precise. And another thing is, it is true that the electron was will escape from the surface. So meaning the photoelectric effect is true. The electrons will be ejected. How electrons ejected? Theoretically, in our first video, we know in order to eject the electrons from the surface, we need to we need enough energy of light to overcome this work function P. So therefore, if you think closer of that, the energy of the light penetrates to the surface, it absorbs. Then after that, electrons will be ejected. So therefore, absorption of light was done during that time. And it is the great evidence of Einstein that a light is a particle. And the photoelectric effect demonstrate the concept on the particle property of light. As the Maxwell says that the light is a wave, and other physicists, Einstein says that light is a particle. And the evidence, one of the evidence is the absorption of light, just like in the photoelectric effect. Other investigation is we have the scattering of light is also the evidence or demonstrates that the particle property of light. Take note again that using this equation we can calculate the amount of work function. So we will calculate that one. This E multiplied with 1.49117 joule coulomb, then the result is 3.29 joules. This is the work function based on our data. And if you look for the value, what is 2.39, which is the closest material, and according to the result, it is very close to sodium. Not exactly a sodium material, but very close to sodium. And it is true that according to the Pasco distributor, that the photodiode is uh, made up very close to sodium, and the absorption of light was proven during this experiment. So our references is the Young and Friedman 2015 University Physics with Modern Physics in the 4th edition, and the experiment process is coming from the Pasco Science Star Photoelectric Effect Experimental Manual. Thank you.